This is the screencast for section 7.3, example 1. Alright, so first we're going to take a look at what volume really means, but basically in this section we are going to be finding volumes of lots of stuff. So first of all, dimension-wise, we know volume has 3 dimensions. 0 dimensions is kind of like a point. It's got no height, no width, no length. 1 dimension is when you take that point and you drag it in one direction, maybe leaving behind infinitely many points. Now that segment has length. 2 dimensions are then when you take that 1 dimension and every little spot on it you drag them in another direction. So now we've got area, we've got both length and width. Then 3 dimensions is when you take every little spot on that area and drag it into a 3rd dimension. So now all this is popping out of the screen. Trust me, it is. So volume then is length times width times height. Now the volume of a rectangular prism is its surface area of one side times its height. So you could take like the surface area of the side here and multiply by the height. So if the height was 1, 2, 3, 4, 5, 6, 7, 8 units, you'd take the surface area and multiply it by 8. Same with a cylinder. You would take the surface area of the circle on the top and multiply it by the height. So in this section, we're going to really focus on what the surface area of a cross section looks like. One little slice of this cylinder, basically one little unit, what it would look like. So for this cylinder right here, it's a solid cylinder, but what if I slice it into a whole bunch of pieces? And eventually I get infinitely many pieces, which will make up the volume of that cylinder. One cross section has a little teeny tiny bit of thickness. Those cross sections slide together to form the full cylinder. So now where's this going? Well, the volume of any solid we want to find is going to be, you take the area of a cross section and you multiply it by a teeny tiny little bit, so a little bit of thickness, and you add all those up from the beginning to end, from A to B. So that is what we will be doing in various ways in this section. So let's take a look at example 1. A square-based pyramid. Now I know you know the formula for the volume of a pyramid, but let's do it the calculus way. A pyramid 3 meters high has congruent triangular sides and a square base that is 3 meters on each side. Each cross-section of the pyramid parallel to the base is square. That's very important. We need to know what the shape of the cross-section is. Then we're going to find the volume of the pyramid. So what I did is the book did, I guess, put the pyramid on the x and y axis, and then, so we said this is a 3 by 3 base, and the base is square, which means somewhere along the x-axis here, because the x-axis comes out in the middle of the base, I'm going to be at the x value x, and that's going to be an x by x base because of similar shapes. So now our cross section we know is a shape of a square. We know that the surface area of, or the area of each one of those cross sections is going to be side squared, or in our case x by x. No matter where x is x is 0.5, it'll be 0.5 by 0.5. If x is 3, it'll be 3 by 3. If x is 2, it'll be 2 by 2. So no matter where it is, the area of our cross section is going to be s squared, which we're going to call x squared then. So to find the volume of this pyramid, we're going to take all of those cross sections, the x squareds, give them a little bit of thickness with a dx, and we're going to stack them from 0 all the way out to 3. And we're going to add them up, and that's what our integral will do. So if I find the integral, use fundamental theorem part 2, I get 9 meters cubed as the volume of this pyramid. Alright, so we're going to start the now try problem number 3 from scratch. The solid lies between planes perpendicular to the x-axis at x equals 0 and x equals 4. So first of all, what does that mean? Well, this solid lies between planes perpendicular to the x-axis. So that tells me that I have the x and y axis here, and then my object is going to be perpendicular, so it's going to be kind of coming away from the x-axis. the cross sections perpendicular to the x-axis on intervals 0 to 4 are squares whose diagonals run from y equals negative square root x to y equals positive square root x. Well, there's square root x and there's negative square root x. So now the question is, what do these squares look like? Well, their diagonals run from one curve to the other. So that means the diagonal cuts through here, and then the squares are running perpendicular to the x-axis. So the x-axis is going perpendicularly through the middle of them. Now this is a full solid. We've only drawn one cross-section of this solid. If you want to imagine what this solid would look like, it's kind of going to be something like this, I guess, where each of the cross-sections is shaped as a square, so it's got like bullets, like a bullet with edges, I think. I don't know what else that shape would be. Maybe one of those nets you put over your lunch when you're out at a picnic so the bugs don't get in. Anybody seen those? No? Okay. Alright, well, we have some basic information here. Now we need to get the area of this cross-section. Well, the cross-section looks like this. There's its diagonal. Its diagonal, the top part here, has a distance of square root x, and so does the bottom. I know it's negative square root x, but its distance is positive because we take the absolute value. So now we can use Pythagorean theorem to find out what a side will look like, or what will what we can use as the expression of the side. So side squared plus side squared equals this 2 square root x squared. A squared plus b squared equals c squared. And I'll multiply, simplify, etc., which means I get that a side is the square root of 2x. One side is the square root of 2x, which means I can find the area of a cross-section now. Cross sections are square, meaning their area is side squared. We found that a side is square root 2x, so we're going to make the area square root 2x squared, which is really just 2x. So again, we took a cross section, we knew its diagonal, we used Pythagorean theorem to use its diagonal to find one of the sides, and then so we solved for side squared. Now let's work on finding the volume of this whole bizarrely shaped object. So this volume then is going to be, we're going to add up all the cross sections. Those cross sections are going to stretch from 0 to 4. That's what we're slicing, 0 to 4. Now each of those cross sections has an area of 2x, and then we're going to give them a teeny tiny bit of thickness, a little dx. Now we integrate. Antiderivative, fundamental theorem part 2, we get 16 units cubed. So this has a volume of 16 cubic inches or 16 cubic meters. And all we did was we sliced the object up, took the area of each times a little bit of thickness, and stacked those all up on top with an integral.